All right, so we're in section 11.2 now.
And the more carbon
So we're just going to add another coordinate to the vectors that we've been working with in the plane, and move off the plane and into 3 dimensions. So when we move off the plane, we construct our z-axis, and we just draw it perpendicular to both the x and the y-axis. So what we're looking at, the way we normally draw our 3-dimensional coordinate system is let me move this down a little bit. Draw it the other direction. There we go. And we can extend this down here, and this back here, and this back here. And normally the way we draw our coordinate system is like so. And we call this is a right-handed coordinate system.
All right. It's something like this, right?
If you put your fingers in the direction of the x-axis and curl your fingers into the direction of the y-axis, so your fingers are in the direction of the x-axis, you curl them into the direction of the y-axis, your right thumb points on the positive z-axis. Or if you think of it as your right hand pointing along the x-axis, your left hand pointing along the y-axis, the z-axis going up through your head. So that's the right-handed coordinate system. If we switch them around, if we would put our fingers of our left hand in the direction of the x-axis and we curl our fingers onto the z-axis, our left thumb would point in the positive z direction, and that would be a left-handed coordinate system. So we're always going to be working with a right-handed coordinate system. So our coordinate system produces, we talk a lot about the 3 planes that we produce when we make a 3-dimensional coordinate system. So we'll talk a lot about our 3, rather than coordinate axes. We'll talk about the coordinate axes as well, but we'll also talk about the coordinate planes. So the xy plane. So the xy plane is where z equals 0. So that's just down here on our normal plane that we've been working with for forever. The xy plane is where z equals 0. The xz plane so that's this plane here. The xz plane is where y equals 0. And we'll also talk about the yz plane, where x equals 0. So that's this plane here. And well, our 3-dimensional coordinate system, rather than talking about quadrants, we'll talk about octants. And the most common one that we'll refer to is the first octant. The first octant is where x, y, and z are all positive. And I refer to octants so infrequently that I can't remember exactly how they're numbered. I think they go counterclockwise. So the first octant is here, the second octant will be back here where x is negative, the third octant over here, and then I'm not sure what happens when you go below the xy plane. But mostly we'll be talking about the first octant. So if we're talking about the first octant X, Y, and Z are all positive. So I'll just and when we're working in a three-dimensional coordinate system, we can say our x coordinate. X is the distance from the YZ plane. It'll be convenient to talk about X, Y, and Z this way for various kinds of problems. Y is the distance from the XZ plane, and Z is the distance from the XY plane. So just a little terminology about our referring to our three-dimensional coordinate system. We'll talk about our three planes a lot. First octant, we'll refer to the first octant on occasion, and it will be convenient to talk about our distances from our coordinate planes this way. All of our ideas about vectors transfer directly over from the plane into three-dimensional space. Distance, midpoint, standard equation of a sphere. We're just adding a coordinate. So all those ideas that we've talked about in the plane transfer over into space. We're just adding the z coordinate to our equations. All of our properties of vectors extend from the plane to 3 dimensions. So equality, length, unit vector, addition, all the things that we know how to do in the plane with vectors transfer directly over into 3 dimensions. There's really nothing different other than adding another component. A couple of things that I wanted to add here is just one in terms of notation. Yesterday we talked about the length or the magnitude. Our book uses the notation, the double bracket notation for the length or the magnitude of a vector. Other books, and the way I learned it, just uses a single bracket. And I think it makes the notation just a little cleaner. So I will use the single bracket notation for magnitude. Just realize it's the same thing as the double bracket notation. Looks like absolute value. The absolute value of a vector is the same as its length or its magnitude. And I think this just cleans up the notation, especially when it's written. These double bars get, when you start talking about the magnitudes of lots of different vectors and you're multiplying them, the double bars tend to get kind of messy. Let's see, one thing that we did not talk about yesterday is vectors, parallel vectors. So vectors are parallel if for two vectors u and v, u is a scalar multiple of v. So this is how we decide if vectors are parallel. Vectors are parallel if one is a scalar multiple of the other. Our standard unit vectors we have I and j from the plane. So our standard unit vectors in space are just going to be, like I said, we just add one coordinate. And so I, our standard unit vector, is going to be the vector 1, 0, 0. J hat is going to be 0, 1, 0. And then our third standard unit vector is k hat. And that's 0, 0, 1. And like we said yesterday for the standard unit vectors in the plane, any vector in space can be written as a linear combination of I, j, and k. So we can make some combination of I, j, and k that will represent any vector in space. So our standard unit vector in the z direction is k hat. There's really not a lot extra to add about vectors in space versus vectors in the plane. It's just really, honestly, it's just adding that extra coordinate. So I just wanted to look at one quick idea that often just gives a little bit of confusion. So let's say we have a cable. Let's say we have a cable, and our cable is stretched between the points, and I'm just making this up here. Let's say it's stretched between the points 1, 3, 5. And the point, or did I say 5 and wrote 3? I surprise myself when I do that. And the point 4, 7, 9. So we have a cable between these 2 points, and we know the tension in the cable. Let's say the tension in the cable is 50 pounds. And we want to represent the tension in the cable as a vector. So anybody have an idea of how we might do this? So let's say our cable is anchored somewhere. It's anchored at this point, and it's holding something up, and what it's holding up is at that point. So we have the points here where our cable is stretched, and we know the tension is 50 pounds, and we want to represent the force. We want to represent the force, this tension in the cable, as a vector. So what did you think, Liam?
So right, subtract each one of the vectors, so you'll have 3I hat plus 4J hat plus 4K hat, and that's your unit vectors. And then I hat should be 50 cosine theta magnitude, and J hat should be 50 sine theta magnitude.
Okay, so I think you're on the right track. So the first part, I'm going to go with the first part. So what Liam was saying is let's turn this. We have these 2 points. Let's turn that into a vector. So we're going to turn these. Our cable goes between these 2 points. So let's turn this into a position vector. So we have a vector that points from one point to the other point. So we have that will tell us the vector along which this tension is acting. So we're going to turn these points. We're going to turn this into a vector. So we'll take this and we'll say the vector between the points is I'm going to say 4 minus 1 is 3I, 7 minus 3 is 4J, and 9 minus 5 is 4K. So this is the vector that points that goes from one point to the other point. It goes from this point to this point. So now I have a vector. I know that the tension in the cable is 50 pounds, and it is in the direction of this vector, right? It can't be in any other direction. The tension has to be in the cable. So if I have 50 pounds and my tension is acting in the direction of this vector, what do I need to do to this vector? What's contained in this vector that I don't want in there? The magnitude. This vector has a magnitude that's the length of this vector. So if I find a unit vector in the direction of this vector and I multiply it by the tension in the cable, that's going to represent the force in the cable and the direction of that force. So how do I find a unit vector in the direction of this vector? Divide by the magnitude. So a unit vector in the same direction is, we're going to say the magnitude of this vector is, we're going to divide by the magnitude, so 1 over the square root of 3 squared plus 4 squared plus 4 squared times 3i plus 4j plus 4. Okay? And does this come out to square root of 41?
Yeah.
Okay. So that's 1 over square root of 41 times 3i plus 4j plus 4k. So that's a unit vector in the direction of this vector that's between the points. And if I multiply that unit vector, it has length 1 now, by the tension in the cable, that will give me a representation of the force in the cable as a vector. And I guess we would then have to decide, is the cable pulling, we'd have to decide on the direction. Which direction is the tension in the cable going? So our tension, our force, so we can represent the force as 50 over the square root of 41 times this vector that is in the direction of the cable. So that there are problems, or there is at least one problem in the homework where you're finding, representing the tension in a cable. The cables are holding something up, and you want to represent the force in the cables as a vector. So this would be the procedure you would follow to do that. Find the vector that goes between the points, and that will give you a vector in the direction of the force, and we need to normalize that vector so its length is 1, and then we can multiply that by the tension to get a representation of the force as a vector. All right, does that make sense? Okay, that's all I really had to talk about today. Let's see, so our homework. So yesterday we had, what, it took 3 lines to write the homework yesterday?
Yeah. Today is very short. It's nice.
There you go.